Hi, thanks for tuning in. If you're watching, you've been flabbergasted. The show where contestants answer science questions for the chance to win credits or no credits. I'm your host, Lab Nudra. Let's go meet our contestants. Hi, I'm your host, Lab Nudra.
And I'm your contestant, Raguru Kamada.
Nice to meet you, Raguru.
Nice to meet you.
Today, our categories are 0-point energy and oh, that's it!
No way.
Your first question is, in one word or less, please describe 0-point energy.
The 0-point energy.
I'm sorry, that's incorrect. The correct answer is perpetual energy.
That's not one word.
I'm sorry, that was a trick question.
What?
I'm sorry, you've just been flabbergasted. Here's your next question. What is the significance of Planck's constant in 0-point energy?
I have no idea.
Let me explain it to you. Are you familiar with Heisenberg's uncertainty principle?
No, sir, I am not.
Well, Heisenberg's uncertainty principle is...
Yes. With this principle.
Heisenberg's uncertainty principle states that it's hard, in fact, it's impossible to precisely measure the momentum of a subatomic particle when you know its position. What does that mean in terms of 0-point energy? Well, think of it this way. Let's say you have a subatomic particle, or an electron, in its lowest energy state, okay? Its lowest energy state, close to the nucleus of an atom. Now, we can tell its position, exactly. But Heisenberg's uncertainty principle states that no matter what, we can take as much energy as we want out of that electron, and still, we will never be able to make it have zero energy, zero kinetic energy. Do you know why? The reason is because we can't predict the momentum of the electron. So even if we take out all the energy when it should be stopped, we can't say that it stopped because we don't know. That was not very clear, but since it's Wednesday afternoon and this project is due Thursday, I'll go on. Now, Planck's constant tells you that uncertainty. I'm sorry, you've just been flabbergasted. So, Mr. Negro, how are you feeling? You've been flabbergasted twice so far out of 2 possible questions. Are you all right?
It feels pretty bad. I'm hurting a lot inside, but I think I can get the next question right.
Good for you.
All better.
Let's hope so, audience. Now, if I were to take a helium atom, for instance, and I were to lower the temperature down to, say, absolute 0, would the helium be A, a solid, B, a liquid, or C, gas?
I think it would be a solid.
You would think so, but you've just been flabbergasted!
What? No. No!
Helium is actually a liquid at absolute 0. Do you know why?
Obviously not, sir.
Helium is a liquid because no matter how much energy you take out of the system of the helium atoms, you can't take enough out for it to be a solid. That's the concept behind 0-point energy. I can just keep on taking photons of energy all day out of the helium atom, but it will never get low enough to be a solid.
No way.
Does this mean you can get energy out of nothing? Yes, it does. Would you like to use a lifeline, Mr. Negruk?
Yes, sir, I would. And for something this ridiculous and
Wait! Before you can use a lifeline, you have to do something. Stand on that table and sing "Ain't No Mountain High Enough." Ain't no mountain high enough.
Ain't no mountain high enough. Ain't no valley low enough. Ain't no river wide enough to keep me from getting to you, baby. And then turn into the grave.
I want to talk about Heisenberg uncertainty principle. We know that if we know position of a particle, we don't know its speed. In fact, we can never truly know the speed of a subatomic particle. That means we can never surely say that its speed is zero. Does that make sense? If its speed is not zero, the subatomic particle has some kinetic energy. Therefore, we can keep taking energy out of the system, keep taking energy out, but we will never, ever make the velocity of the particle zero, which means it will always have kinetic energy, which means an unlimited source of energy. That is the origin of zero-point energy theory. Now, I want to talk about three more things. The first is the Casimir effect. When you bring two metal plates, very thin metal plates, as close to each other as you can, about a couple atomic diameters away, you start to see that they will attract each other. And in fact, they will bind together. You could say this is van der Waals forces, but another way to explain it is zero-point energy. Now, the electrons in the atoms of both metal plates are vibrating. Okay, think about a mass on a string. It vibrates and vibrates and vibrates. The electron vibrates the same way, and you get a magnetic field, an electromagnetic field. Now, there's an electromagnetic field on one plate, an electromagnetic field on the other plate, and they line up and they correspond, and they polarize each other, and they connect. That's how you get electromagnetic attraction. Now think about this everywhere. Every point in space has zero-point energy. Every single particle in space has vibrating electrons. So that means there's literally millions and millions of magnetic fields, little small magnetic fields. So many, in fact, that the total energy from zero-point energy in the universe is 110 orders of magnitude greater than the energy density of the sun. I mean, that's a lot of energy. Let's take this one step further. I want to talk about inertia for a second. What is inertia? What is mass? Mass seems so arbitrary, so unexplainable. I mean, how come something that's heavy is harder to move? It doesn't really have any real reason, but zero-point energy provides some reason, maybe. Since there's so many millions of electromagnetic fields around, an object of a high mass is affected by this electromagnetic drag force, meaning there's forces on all sides pushing it, affecting it in different ways. So it slows down. It's called the electromagnetic drag force. Now, I mean, this is very new stuff. We don't know if it's true, but it might explain inertia. And to be honest, we don't really know what mass actually is, what inertia actually is. Newton just said it. I don't even think he knew what it meant. He just said it's some innate quality of objects. So zero-point energy has some pretty interesting potential applications. Yeah. So, I mean, everybody's gonna get into it. Energy for nothing seems like a pretty good deal. Let's see what happens in the future.